group 17, the halogens, and we'll be looking at trends in properties, specifically trends in electronegativity and the boiling points. Again, if you've been watching me, you'll know that I like to kind of blurt some summaries at the beginning before we get into the more in-depth content. So we'll just start by saying that the boiling points increase down the group. Bear that in mind. Whereas the electronegativity decreases down the group. And we'll talk about why now. But yeah, I'm going to grab my highlighter and remind myself. So let's start by reminding ourselves what the term electronegativity means, because otherwise we won't understand why electronegativity decreases down the group. So in case you're asked to define this, electronegativity is the power of an atom to attract a pair of electrons towards itself in a covalent bond. So if we consider that definition, the power of an atom to attract a pair of electrons towards itself in a covalent bond, what's going to be doing that attracting is obviously going to be the positively charged nucleus. So ideally speaking, you want a small atom, don't you? So that attraction force is stronger. So to really spell that out, electronegativity decreases down the group because there is an increasing distance between the nucleus and bonding pair of electrons, and that's due to increased shielding. Remember, these are the group 7 or group 17 elements, so we're starting at the top with fluorine, chlorine, bromine, iodine and astatine. According to what we've just said then, fluorine is the most electronegative. Astatine is the least electronegative. And remember, this goes some way to explain why fluorine can be involved in hydrogen bonding, because remember, hydrogen bonds form between hydrogen and highly electronegative elements, which you have to learn, remember, are fluorine, nitrogen and oxygen, and that's the only time hydrogen bonds will form. What about if we consider the boiling points now? So the boiling points of group 7 increase down the group. Don't just rote learn these things, guys. Just remember to use facts that you're probably already aware of. So the fact that fluorine and chlorine are both gases, bromine is a liquid. Remember, we're talking at room temperature here. Iodine and astatine are both solids. So that tells us automatically that the boiling point increases down the group. But why is that? Well, it's because the number of electrons, and therefore the number of electron shells, increases down the group. Fundamentally, that means that the halogen molecules, because remember, they're all diatomic molecules, this means that the molecules are larger. And then if we consider intermolecular forces, the intermolecular forces that are important here are the van der Waals forces. So with the molecules being larger, there's a larger electron cloud to distort. So we're going to say that there's more van der Waals forces. Which require more energy to overcome them. The boiling points of the halogens increase down group 7 because the covalent bond strengths increase. No, remember, with the boiling points, you're breaking intermolecular forces. Covalent bonds occur within the molecules, so that's not the reason. Bond polarities increase. Again, that's false. You've got two of the same atom, haven't you? The surface area of the molecules increases. Remember, that's true because as you descend that group, the atoms have more shells for electrons. The electronegativities increase. No, that's false. They decrease down the group do make sure you go through the other options if you're not entirely sure, just proving why they're all wrong, and that will help you zoom in on the right answer even if you're not 100% sure. Explain why chlorine has a lower boiling point than bromine. So chlorine is a smaller molecule with fewer shells of electrons, so fewer van der Waals forces between molecules. So less energy is needed to overcome them. Remember, oxidizing agents cause other substances to be oxidized, which means to lose electrons. And by definition, therefore, oxidizing agents are themselves reduced at the same time, which means they must have gained electrons. Always bear in mind what's happening with electrons in these sorts of reactions. Now, just to recap a little bit, remember halogen displacement reactions from IGCSE and GCSE, because this is tightly linked. At GCSE, you learnt that a more reactive halogen displaces a less reactive halogen, or halide ion, really. So just remember, fluorine is the most reactive halogen, and then as you descend the group, the elements become less reactive. So we can say that if fluorine was to react with sodium bromide, the fluorine would displace the bromide to form sodium fluoride plus bromine. So that's all balanced, and I've added state symbols. If we look at the ionic equation, just if you're not happy with this, just draw out all the ions like this. So I'm separating out those ions. So now you want to delete the spectator ions, so look to see which ions remain the same on the left and right hand side. They are spectators. So our final ionic equation looks like this. So for F2 to become 2F minus, it must have gained 2 electrons. So it must have been reduced. For 2Br minus to become Br2, it must have lost 2 electrons. So that has therefore been oxidized. So we can see how these are therefore redox reactions, because both reduction and oxidation have taken place. So just to really point this out then, because that fluorine has been reduced, remember what I said at the start, by definition an oxidizing agent must be reduced. So here's our oxidizing agent in this case. Remember, they could ask you about color changes. So in this case, that bromine will be orange. If chlorine had been produced, it would be pale yellow or green, and then iodine would produce a brown solution. So here's a summary of all the halogen displacement reactions. So remember, a more reactive halogen will displace a less reactive halogen from its compound, which is why you always get a reaction with fluorine, because it's the most reactive. So for example, it will react quite happily with sodium chloride, sodium bromide, sodium iodide. Chlorine is less reactive than fluorine, hence why you get no reaction here, but it's more reactive than bromine and iodine. Bromine is only more reactive than iodine, so that's the only time you get a reaction. Iodine is the least reactive compared with these elements, so you'd expect no reaction. So to really summarize what I was just saying and make it very centric to A-level and IB, we're going to say halogens react by gaining electrons. So by definition, the halogen is reduced, such as in the case here. Halogens therefore act as oxidizing agents. Remember, I've already said that as you descend the group, the elements become less reactive. That means they also become weaker oxidizing agents. So fluorine is the most reactive and the strongest oxidizing ability. Astatine has the weakest oxidizing ability. As you descend, group 7, oxidizing ability decreases. Chlorine behaves as an oxidizing agent in the extraction of bromine from seawater. In this process, chlorine gas is bubbled through a solution containing bromide ions. Write the simplest ionic equation for the reaction of chlorine with bromide ions. So there's Cl2, there are the bromide ions. Chlorine is more reactive or acts as a stronger oxidizing agent, so actually you're going to produce bromine plus chloride ions. Make sure that's balanced. State one observation that would be made during this reaction. While we make bromine, so we'd see an orange-brown solution. In terms of electrons, state the meaning of the term oxidizing agent. Causes another substance or species to lose electrons. Which of the following is not a correct trend of group 7? The first ionization energy of the atom decreases. That's absolutely true because remember, those atoms get larger, they have more shells of electrons, so it's easier to remove an electron. The oxidizing power of the element increases. No, we said it decreases. We said that at the top of that group, you'd find the strongest oxidizing agent. The electronegativity of the atom decreases. That's true. Remember, fluorine is the most highly electronegative element in that group. The boiling point of the element increases. Yes, remember, astatine and iodine at the bottom of the group are solids at room temperature compared with fluorine and chlorine, which are gases. Which of the following statements is true? Bromine liberates iodine from aqueous sodium iodide. That's true because bromine is more reactive than iodine or is a strong oxidizing agent. We're now going to consider their ability to act as reducing agents. And underpinning this, remember, is the fact that by definition, if something acts as a reducing agent, it must be oxidized in the process. So I'm going to write that. The halogen is oxidized, which remember means that it loses electrons. So bear that in mind the whole time because it will help you understand what's going on when we look at the huge number of equations. So starting with the bold statement that the reducing ability, so their ability to act as reducing agents of the halide ions increases down the group. So if we consider the elements, fluorine, chlorine, bromine, iodine, astatine, by definition, astatine is the strongest reducing agent. Whereas fluorine is the weakest. But what is our explanation for that? Well, as you descend the group, remember the atoms get bigger, so the number of shells of electrons increases. This means that the ionic radius increases. The amount of shielding of those outer electrons, those valence electrons, increases. the electrostatic force of attraction between the nucleus and valence electron weakens. And then the all-important point, which is that the valence electron is more easily lost and that takes us back to our original definition of oxidation, which is all about losing electrons. So the halide ion is more easily oxidized. The halide ion acts as a stronger reducing agent. So if you're asked in the exam to explain why the reducing ability of the halide ions increases down the group, you need to be talking about the number of shells of electrons increasing, meaning the amount of shielding increases, so the attraction between the nucleus and the valence electrons weakens, that valence electron is more easily lost, the halide ion is more easily oxidized, the halide ion acts as a stronger reducing agent. And now let's talk about observations. So how do we observe, or how can we see that the reducing ability of the halide ions increases down the group? Well, we react those solid sodium halides with concentrated sulfuric acid. Bear in mind that we can prove that the halide ion's reducing power increases if we look at the various equations involved and we consider sulfur's oxidation number. Because the greater that decrease in oxidation number of sulfur, the greater the halide's reducing power. Let's take these various halide ions in turn then. So we're going to descend the group starting with sodium chloride, so the chloride ion. Remember, we're expecting as we descend that group that this chloride ion will be a weaker reducing agent compared with the halogens, which are lower down in the group. And we're going to prove that now. So the sodium chloride reacts with that concentrated sulfuric acid, and you will need to learn these equations. In terms of observations, we will see steamy fumes of HCl produced. In red, I'm going to put the oxidation numbers. So hydrogen is +1, oxygen is -2, which means that sulfur here is +6. What about on the right-hand side? Sulfur is again +6, so I'll highlight that to show that there's no change in oxidation state, indicating that the chloride ions are very weak reducing agents. Just as an aside, by the way, we can infer that this is not a redox reaction. And it's actually because that oxidation number of sulfur hasn't changed, so we can't say that oxidation and reduction have both taken place here. So we've dealt with sodium chloride. Moving down a halide ion, we're going to take on sodium bromide. Here, two reactions take place. Here's the second reaction as an ionic equation. And now let's look at the combined full equation for that second reaction. I'm going to label various oxidation states. So in this equation up here, in that first equation, look, that sulfur hasn't changed its oxidation state. So again, it's not a redox reaction. But if we look down here, I'm just going to grab my highlighter. We can see that sulfur's gone from +6 over here to +4 over here, which means that reduction's taken place. The The bromine's gone from -1 over here to 0 here, so that means oxidation has taken place, and therefore we can say that this is a redox reaction. Really spelling this out. So that is oxidation, this is reduction. In terms of observations that take place, we produce Br2, so we will see a brown liquid. Now we're considering the iodide halide ion in the form of sodium iodide. Well, we have multiple reactions taking place here. So that sulfur hasn't changed oxidation state. There's no redox reaction in this first reaction. Reaction 2 now. So there's reduction taking place because we've gone from +6 on sulfur to +4. Looking at iodine, we've gone from -1 to 0, so that's oxidation. So this is a redox reaction. Our observation here is a choking gas, which is sulfur dioxide. Reaction 3. There's sulfur being reduced again. There's iodine being oxidized. So that is a redox reaction. Our observation here is that sulfur produced is a yellow solid. I promise we're nearly there. What about equation 4? So our sulfur has been reduced, its oxidation has fallen from +6 to -2. The iodine has gone from -1 to 0, so that's oxidation, so another redox reaction. In terms of observations, we get a black solid, which is I2. We also get an eggy smell from this stinky hydrogen sulfide gas. And just to bear this all in mind, remember this series of equations is showing to you that as you descend group 7, those halide ions become stronger reducing agents. Question 1, which of these species is the best reducing agent? So 2 things to notice. First of all, we need a halide ion, not the halogen. And second of all, we want the element which appears lowest in group 7, so that will therefore be the iodide ion, I-. Which one of the following statements concerning halogen chemistry is true? Sodium chloride produces chlorine when treated with concentrated sulfuric acid. This is why I said it's so important that you learn these equations, because that first equation I showed you did not have chlorine being produced. Sodium chloride produces chlorine when treated with bromine. This is all to do with halogen oxidizing ability. Do you remember when we looked at a previous video to do with halogen displacement? So a more reactive halogen displaces a less reactive halogen. Bromine is less reactive than chlorine, so this is false. Sodium bromide produces bromine when treated with concentrated sulfuric acid. That's true. That was in the sodium bromide set of equations that I've just written about. Sodium bromide produces bromine when treated with iodine and aqueous potassium iodide. Again, that's false for the same reason that this one was false. So the answer here is C. Concentrated sulfuric acid can be reduced by some solid sodium halides to H2S, give the oxidation state of sulfur in H2S. So remember, hydrogen ions are always +1. The compound is always neutral, which means that the answer here is -2. Give one solid sodium halide which will reduce concentrated sulfuric acid, forming H2S. Remember, it's the elements that sit lower in that group which have a stronger reducing power, so NaI is a good answer here. State 1 way in which the presence of hydrogen sulfide could be recognised. Remember, it's by its horrible smell of bad eggs. A different solid, sodium halide, reacts with concentrated sulfuric acid without reduction, forming a halogen-containing product X. Suggest an identity for X. So you want a halogen which acts as a weaker reducing agent, so you need to look towards the top of the table. So the solid sodium halide will be something like sodium chloride or sodium fluoride. So in terms of what will that product be, it will be hydrogen chloride or hydrogen fluoride. Identify the solid sodium halide which produces X. Already answered that, NaCl. State the role of sulfuric acid in the formation X. It's acting as an H+ or proton donor. So we need to be aware of the tests for chloride ions, bromide ions and iodide ions. In terms of the method, which you do need to specify, number 1, you need to add nitric acid. And they could ask you why you do that, and that's in order to remove any other carbonate ions which could interfere in the test. And the second step is to add silver nitrate. Now this is really important. So if we look at the results, which again you'll have to specify, if you have chloride ions, the result here will be a white precipitate. And make sure you remember to include the word precipitate. Now if you have bromide ions, you'll see a cream precipitate. Sorry, I'm struggling to draw cream. And lastly, if you have iodide ions, then you'll see a yellow precipitate. Now one thing I wanted to just point out to you to help you remember these colours is as you descend group 7, so from chloride here to bromide underneath and then iodide underneath, notice that the colours get darker. So we go from white to cream to yellow. So make sure you pick those out of the periodic table over here to help you. Remember that they get darker, and lastly that they are colours of dairy. So I like to think of it in terms of white milk, cream coloured cream and yellow butter, and that really helps me remember those colours. Now let's look at the ionic equations. So number 1, when we were testing for the chloride ions, now if we look up, we know we're adding those chloride ions to silver nitrate. The nitrate ion here is acting as a spectator, so we're only interested in the silver part of this. So if we add silver ions Ag+ to the chloride ions, which is Cl-, they're both in aqueous solution, so that's our state symbol. They're going to form a precipitate, so a solid, of silver chloride, which we know is a white precipitate. If we take our bromide ions, if we take our silver ions and we add it to those bromide ions, also aqueous solution, we're going to make solid silver bromide, which we know is a cream precipitate. And then lastly our iodide ions, which we're going to add to silver again. And our final solid is silver iodide, which is a yellow precipitate. In reality, however, these dairy colours are hard to distinguish. So at A level, a further test is needed. You add ammonia, and what you find is that when you have silver chloride, the silver chloride dissolves in dilute ammonia according to the following equation. Here's our precipitate. Here's our dilute ammonia. With silver bromide, you find that it dissolves in concentrated ammonia. And they will expect this level of detail from you. And then what really distinguishes the silver iodide is that it doesn't dissolve in either concentrated or dilute ammonia. It is insoluble in both. How about the uses of chlorine and chlorate? Chlorine reacts with cold water to form chloric acid and hydrochloric acid according to the following reaction. So here's your chloric 1 acid. If we check the oxidation states, chlorine goes from 0 to +1, and over here it becomes -1. As the chlorine is both oxidized and reduced according to the increase and decrease of those oxidation states, we say that a disproportionation reaction has occurred. We can use the chloric 1 acid here to kill bacteria. We can use it to make bleach. As we can see, it's a reversible reaction. And then in sunlight, another reaction to be aware of is when chlorine reacts with water to form hydrochloric acid and oxygen according to the following equation again. Now, chlorine is obviously a toxic gas, but if used in very small quantities, it can be used in water treatment to disinfect water and kill any bacteria present, which could be pathogenic. And now a third reaction, chlorine reacts with cold dilute aqueous sodium hydroxide to form sodium chloride, sodium chlorate 1, and water. Check our oxidation states again. Chlorine goes from 0 to -1 over here and +1 over here. So it's another example of a disproportionation reaction because it's being both oxidized and reduced. And this sodium chlorate here is another active ingredient in bleach.